All right, today's lecture is on impulse. Impulse is another kind of quantity of motion which is sometimes useful. It's defined as the force times time. Here's an example of impulse. Imagine a car traveling with some initial velocity called v sub I, right, and driving into a tall grassy field, right, and allowing the grass, right, to slow the car down until it comes to a complete stop sometime later, right?
Yeah.
So its final velocity is 0. Now imagine starting out at the same initial velocity in the same car and using a brick wall to slow yourself down, right? What's the difference in these two? Well, recall that force can also be written as delta P over delta T, right? And so if we define force times the time, or force times delta T, as the impulse, then you can see that the impulse is also equal to the change in momentum, okay? So in both cases here, right, the momentum went from an initial state, where the car had some mass m and some initial velocity vi, and in the end it still had mass m, but its velocity was 0, right?
Yeah.
So the change in momentum is the same in both cases here, right? Delta P1 is equal to delta P in 2. Well, this is Roman numeral 2, Roman numeral 1, right?
Yeah.
So the change in momentum in both cases is the same. So what's the difference in these two pictures, right? Well, which one would you rather be in?
Grass.
Car 1 or the car in case 2?
Case 1.
Car in case 1, right?
Yep.
Coming to a nice gentle roll. So what's the difference here? Well, in this case, the force is rather small, but the time period, delta t, is rather large. So over here, even though the impulse is the same amount, right, it's a small force times a big delta t, right? Because it took a long time for this car to come to a stop, right? Whereas in this case here, we have a huge force and a little tiny delta t. You see?
Yeah.
So in one case, it's the force which is big, and in the other case, it's the delta t that's big. Okay?
Okay.
So that's the difference between these two cases. Another way to think about impulse too is that if you really want to change the momentum of something, right,
Yeah.
then you apply a force for a longer period of time.
Okay.
So if I apply a force F, right, say it's just, 1 Newton is about the force that you push with on your finger like this, right? It's about a Newton. If I do that for 1 second versus 100 seconds, right?
Yeah.
At 100 seconds, I can accelerate something quite quickly, right?
Yes.
I can bring it up to a very high velocity if I apply a force of 1 Newton for 100 seconds. Whereas for just 1 second, right, it's not going to be at a very high velocity in the end, right? So I don't change its momentum by much if I'm just doing it for 1 second. So, interestingly, rockets, or model rockets specifically, right, the engines for model rockets are designated by their impulse. And so if you get a rocket motor that says an A on it, A corresponds to 2.5 Newton seconds of impulse, okay?
Okay.
Remember, newtons are the unit of force, and seconds are the unit of time, and so impulse, force times time, will have units of Newton seconds, okay?
Okay.
Whereas a B motor will have 5 Newton seconds of impulse. A C motor will have 10 Newton seconds of impulse, okay?
Okay.
Now there are some more numbers that usually are given to you for a rocket motor. You might have like a B10 or a B5, and what that's going to tell you in the end is ultimately what the time, the burn time is, how long the motor is going to burn, okay? And so you'd use, if it said B10 for example, you'd say, okay, well I know that B is a 5 Newton second motor, right? So a B10 must be, the 10 means 10 newtons, okay?
All right.
And since I only have 5 Newton seconds, that means that the burn time is going to be 1/2 second, you see?
Yeah.
So you figure out the burn time for that. But here I'm going to give you some burn times, and we'll just use these kind of stock numbers here. So let's consider how we can figure out what the final, or the maximum speed of the rocket is, okay? So we know that delta P, which is going to be equal to the impulse, right? That'll be equal to the final mass times the final velocity minus the initial mass times the initial velocity, okay?
Okay.
Now the initial mass will actually be bigger than the final mass, because the final mass will reflect the fact that the rocket has burned some of its mass in propellant, okay?
Okay.
But we're not going to worry about the details of that. The initial velocity, however, is almost always going to be 0, because we usually launch these things from some launch tower, and they'll be sitting still on the ground. So since the initial velocity is 0, we don't even really need that at all, okay?
Okay.
And so this is going to tell us that delta P is going to be equal to the final mass times the final velocity. And from this I can solve for V sub F, and that will be delta P over the mass. Okay?
All right.
So we need some numbers for this now. Let's assume that our final mass, so that's the mass of the rocket after it's already burnt all of its propellant. And you could get this by, if you already had a rocket motor that you've already used, right? Stick it in the rocket, weigh the rocket. That'll be its final mass, okay?
Okay.
Well, let's assume that m sub f, it's right over here, m sub f is equal to 50 grams, okay? Not far off for a model rocket. And let's consider what's the final velocity if we launch with an A motor and maybe also a B motor, and see what the difference is going to be, okay? Well, actually, let's do a B and a C motor. I think that would be, for starters, it would be easier. So if we launch it on a B motor, also I'm going to assume that the burn time, TB, is going to be equal to 1 second, okay?
All right.
I'll write that SEC so it's clear it's a unit. I think that's all the inputs that I need. So now this final velocity is going to be also going to be the maximum velocity of the rocket, right? It's never going to be going faster than it is at the moment its motor burns out, okay?
Okay.
So what happens is it's going to accelerate up from the rocket thrust, right? Getting faster and faster and faster. And then the rocket motor turns off, burns out. That's what we call it burnout time, right? And now it's coasting, right? So it's got its maximum velocity. It's still going up, right? But gravity, of course, is accelerating downward, right? And it's going to cause it to slow down. So its velocity will decrease until it gets a velocity of 0 at its apex, and then it'll fall back down to the Earth, okay?
Okay.
So we can also call this V final. We can see that this is the V max, okay? That's the maximum velocity of the rocket. So for a B motor, right, this V max is going to be equal to, well, delta P, that's just the impulse, right?
Yeah.
And an A motor, or excuse me, a B motor has an impulse of 5 Newton seconds. So that is 5 Newton seconds divided by the mass, right? Final mass, which is 50 grams, so that's 0.05 kilograms, and that is going to give us 100 meters per second. Okay?
Okay.
That's its final velocity, 100 meters per second. That's about 230 miles per hour. That's pretty quick, huh?
Yes.
If we launched on a C motor instead, right, then Vmax would be equal to 10 Newton seconds, because the impulse of a C motor is 10 Newton seconds. I think I mentioned that these always double, right? So a D motor would be 20 Newton seconds. An E motor would be 40 Newton seconds, so on and so forth, right? The biggest motor I've ever launched a rocket on, I think, was a J motor, which is right around 1,000 Newton seconds, okay?
Okay.
So, but anyways. So Vmax for this, still I'm going to assume that the burnout mass is the same. In reality, they're going to be a little bit different, right? Because the motor itself is a little bit bigger, okay? So if it's the same rocket, and I use, say, a B and then a C motor, the burnout mass will be just a little bit different, but we'll assume it's the same, okay? And so this will give me, of course, 200 meters per second.
All right.
So 460 miles per hour. Pretty fast, right?
Yes.
Now, of course, we're completely neglecting air resistance here, right?
Yeah.
And I'm not going to include air resistance in these calculations. Let me just say it will at least cut these numbers in half, okay?
Okay.
Because the air resistance that you feel is proportional to the square of the velocity, okay? It's also proportional to the cross-sectional area of the rocket, the density, and then your rocket shape will determine a drag coefficient that you'll have to use in there as well. But anyways, it's going to reduce these velocities and also altitudes quite a bit, okay?
Okay.
So what we're going to do now, we've got these maximum velocities, right? So that, of course, is, during the boost phase, right? And I'm going to kind of draw this up at an angled flight, right? This is the boost phase, right? And so here at this point, right, we're at Vmax. I should draw that a little bit bigger. So right here is burnout, right? There's my little rocket. And that will be V max, okay?
Okay.
Now what's it going to do? It's going to coast for a bit, right? Until it reaches its, its apogee, right? Its maximum altitude, okay? So how do we figure out how far it's going to coast? Well, first we have to figure out how far has it traveled so far. Well, at the end of this, at burnout, it's traveling at this maximum velocity. But it wasn't traveling that fast the whole way, so I can't use that times the burn time. Right? I know the rocket fired for 1 second. So this is how far does the rocket go after 1 second, right? So what is the quantity of motion that we use to figure out how far something travels? You want to remember from kinematics? Right? What is the right thing to use to figure out how far something travels?
I need several things, though.
Well, I know the time. It's going to do something for it's going to travel for 1 second, because that's the burn time of the rocket, right?
I know the speed and the angle it's...
Well, you can't use the max speed, right? Because it wasn't traveling at this speed the whole time. If I use the max speed times 1 second and said that it's traveled, 100 meters, that would be wrong, okay? Because when it started out, it was going 0, okay?
Okay.
But what I can use is I can use the average velocity. Right, started out at 0, it ended at 100 meters per second, right? So the average velocity, which we'll call V average, like this, okay? And I'll put B here for a B motor, will be equal to 0 plus 100 meters per second divided by 2. So that's 50 meters per second. That's its average velocity, okay? And the average velocity for the C motor, on the other hand, would be 0 plus 200 divided by 2, which is equal to 100 meters per second. So what that tells us is that the distance that this traveled, right, and I'm going to assume that it's actually traveling straight up in the air, okay? But the distance that it traveled up in this direction, right, we'll call this D sub B for the burn distance, right? The distance it traveled to burn out, I'll maybe a BO, like that, right? This is going to be equal to the average velocity times the burn time, right? T sub B. So in this case, D sub BO will be equal to 50 times 1 second, right, which is equal to 50 meters. And for the C motor, right, D sub BO will be equal to 100 times 1, which is 100 meters. Okay?
Okay.
So that's the distance that it traveled during the burn time while the engine is firing. Okay?
Okay.
And I use the average velocity to get that distance. Okay?
Okay.
Now I want to figure out how far it's going to coast. And if you go back to lecture 6, right, in lecture 6 I derive an equation, right, this last part of it here, right, this last distance, which we'll call delta x, right, we can get this from the following relationship. 2 times gravity times delta x is equal to v final squared minus v initial squared. This is a kinematic equation that I derived in lecture 6. So you can go back and watch that and see how I did that. Alternatively, you can use the old way of doing it. You can say, well, I know its initial velocity is v max, right?
Yeah.
And its final velocity is 0.
All right.
And I can ask, well, so the time that it takes, when is it 0? Well, whenever what's the time period of this travel? Well, I figure out how long it takes before it gets to a velocity of 0 using the acceleration of gravity, right?
Yeah.
And then I use that to figure out how far it's traveled in that time period. But this combines both of those calculations into it, and so we can just use this equation here. We solve for delta x, right? So in this case, our v initial, right, will be the maximum velocity, right?
Yeah.
So we'll get that delta x is equal to, the final velocity will be 0, because that's at apogee, right?
Yeah.
And so we'll have a negative v max squared divided by 2 times g, but remember that g is negative because this is accelerating in the downward direction, so that'll kind of cancel the sign of this guy out. And the acceleration due to gravity we'll use in meters per second, okay? And we'll say that it's about 10 meters per second.
All right.
And 2 times 10 is 20, so we'll do 20 meters per second squared, okay?
All right.
So if I now plug in what delta x for, say, a B motor is, right, that's going to give me V max, which I'll use this here, that's 100 squared divided by 20, and that's going to turn out to be, that's 10,000 divided by 20, I believe it comes out to be 500 meters. Okay? And for the C motor, right, this distance is not 100 meters per second squared, but 200 meters per second squared, right? 200 squared over 20, and this will be 2,000 meters. Okay?
Okay.
And so the question now is, what's the total height, right? What's its maximum altitude, of the altitude of apogee, right? Well, you just add these numbers to the distance they traveled during the boost phase, right?
Yeah.
So the B motor, right, we'll say altitude of the B motor, right, will be the D sub B O plus, well, let's say altitude is equal to the D, the burnout distance, plus delta X, the coasting distance, right? And so for a B motor, we would get 50 meters plus 500 meters, which gives us 550 meters. And for the C motor, it's 100 meters plus 2,000 meters, which is 2,100 meters. That's terrible. Meters. Which is about 1 1/3 mile up. Okay?
Okay.
Now, again, reality, half that, at best, because of drag from air resistance. Because especially when you're going fast, right?
Yeah.
And these rockets can go really, really fast. If you put these rockets on, maybe an M motor, for example, they're going so fast that if you were to paint the nose cone, for example, that would all melt off. If you were to use a plastic nose cone, it would melt. So you have to use something like, you could use metal, like titanium. The body, you'd want to use carbon fiber, because the friction, the heat from the friction is going to be so high that it would melt it if it was anything other than that. Or you can make it out of aluminum, of course. Okay?
Okay.
So, impulse, right? It tells us what the change in the momentum is going to be. Okay?
Okay.
And we've used it here to show how high a model rocket will go and considered for a B motor and a C motor.